So I've had this video in the back of my mind for quite a while. I have noticed something rather recently in a recent video when it comes to the 91-mile-an-hour shrimp rigger. And a couple things had happened, and it prompted me to start researching, doing a couple things, and just overall research. And throughout my research, I learned some things, and from these things I wanted to share with you. And we've got a whole lot here. So we've got a king valve, basically like a rocket motor, TP motor, Oxydine motor. We've got this dynamite motor, this little TP motor, and then this little motor here in a Traxxas Bandit, which the motor that is in here is a tiny little, I think it's a 3650. It's just the cheapest brushless kit you can buy off Amazon for this car. Now, why are we talking about cars and boats? There's a reason. We have something called axial load and radial load. Now, if we talk about boats, we're always dealing with axial load. Now, that load comes from the prop pushing forward. It's propelling the boat forward. Now, all of this thrust that's pushing forward, what takes that abuse? The motor takes that abuse. The driveline takes that abuse. The bearings inside the strut take that abuse. Now, in the previous video, if you go back and watch, and I may throw it in here just to show you what was happening. After I had brought it back from a high-speed run, I noticed that the motor was loose. So we've got the motor here, right? Well, watch this, watch. Isn't that nutty? Look at that. It's like the whole end bell of the motor's come off. What? Now, the bolts were tight up front. The collet was tight. But you could take the motor and you could wiggle it. Now, most motors, when you come over here to, say, the Oxydine motor, the front end bell is held on with these screws. The whole front plate. Even the back plate is held on with these Phillips head grub screws. Come over here to the TP motor. We have 4 Allen bolts that hold on the front end bell. And on the back, we have these grub screws that go around it here. That's what hold on this bottom gold piece. As for the cheaper rocket motors, these are held on with a grub screw here, a grub screw here, and here. Same for the back. That prevents the back from coming off. That's what holds it on. Now, when we come to this motor here, the same thing can be said. We've got this grub screw here, and we've got this grub screw right over here, and we've got 1 and 2 more hiding on the other side. Now, in a minute, we're going to take this off, and I'm going to show you exactly what's happening to this motor, is what prompted this video. Now, I don't know if you can tell based on the video. Let's see if I can get a really, really good close-up of this. But right here, let's see if it'll zoom in. Yep. If you notice, see the gap right there? Okay, this end bell is supposed to be sitting flush with this black can of the motor, and it's not. And another thing, if you can tell, this grub screw, see right here, right in front of the file tip? See how that grub screw kind of seems like it's being bent at an angle? That's because it is. The axial load coming from this prop is putting so much thrust through the driveline that it's loading up the bearing on the back side of this motor, and it's trying to push the center rotor, which is this, it's trying to push this out of the back of the motor. Now, when you talk about RC cars, you don't have axial force. You have radial force, which is perpendicular to the motor. So what we have here is we have this gear set, and the gear set runs through the spur and the pinion, which through the transmission down to the drive axle to the tire. What this does, it actually loads up the bearing here. So we have this bearing here, and we have this bearing here. Well, rather than putting, say, downward force, if this motor was sitting like so, actually we can use this like this. If this motor was sitting like this, axial load is pushing straight down on it. Radial load, like on an RC car, is pushing down on it like this, which that's the way the bearings are actually designed to handle the load in these brushless motors. Radial load. Now, the front bearing under radial load with a car, the front bearing helps support it here from pushing down, and the back bearing helps support it from pushing up. And no problem. You know, over time, those bearings will wear out. You pop new ones in, you're out $10 and you save a $100 motor. But when it comes to boats, the axial force is going to be something different. Because how can you prevent that from happening? Now, there's a few things, and I've yet to try this, but they sell these things for a reason, and it'll be the first time trying them. Now, these are thrust bearings. If you notice here, you've got one center bearing. It's basically a bearing in a race. The two races are separated. Let's go ahead and flip this over so you can actually get an understanding. So both of these are grooved in such a way to where the balls will ride in the center. And what this does, these pieces go on the end of the motor here. You'll have the bottom plate will go on first, then you'll have the ball plate, and then you'll have the top plate go on there, and then you'll slide your collet on. So when you have axial force pushing into this motor, trying to push the center rotor out of the back of it due to the thrust of the prop, all of that load can then be put on this thrust bushing, this thrust bearing, right at the collet. And I'll show you that here in a second. Now, if you don't have these, and you don't necessarily need these when you start talking about bigger motors that can actually handle the stress. I've never seen this happen except on this 2968 TP motor. It's the biggest 29 millimeter motor that they have at TP, but I've never seen one do this. And the front of this motor is different. It does not have grub screws. The end bell is threaded onto the can. And what I noticed when I originally took the motor out trying to diagnose the issue is that the threads on the gold front housing that are male thread into the female threads in the black portion of the can had actually popped the threads out. It had pushed so hard that it had pulled the aluminum threads forward or back, however you want to, see it. But basically it took the black can because the silver part of the face of the motor is stationary. It's locked in by those two bolts. And when I was able to move it, because the threads on the front and the can weren't tight anymore because they had pushed one thread forward, which was crazy. Now what that ends up doing, that ends up moving the rotor inside, like away from the magnets. Like they ride in such a specific area inside the motor, and you have to have shims to shim it perfectly. Now, that's what these are over here. So these are your shims. And I've got these out just for an example, but you can tell just how thin that shim is, then that shim, and they progressively get bigger. So if you ever disassemble a brushless motor, you need to pay attention to the orientation of the shims as they come out, so you can install it and have the same pattern. I made a mistake on this dynamite motor. It was the first one I learned on, and when it came apart, that's the rotor for it. The motor's fine. I lost all the shims. I knocked it apart and then they flew everywhere and I didn't know the orientation. I tried putting the motor back together and it just doesn't run right. It doesn't run like awful. It doesn't have as much power as it should. And that's because it's not riding beautifully in the middle. It's either riding somewhere like this or it's riding somewhere like this. So it's not, you know, smack dab in the middle. Now, what I'm going to do, we're going to go ahead, we're going to take out this 4220 TP motor out of here, and we're going to go ahead and take a look at it. And I'm going to show you exactly what's going on. Okay, so we've got the motor taken out of the shrimp rigger, and it is sitting right here. Now, I've taken the liberty of measuring the gap on the back here, and it's a smidge over 30 thousandths of a gap. So I don't know if you can tell in the video, but that grub screw is literally at an angle. It is cocked back. Let's see if I can stick an Allen wrench in there and show you just how much. See that? See how much of an angle it's cocked back? They've all done it. It's trying to push it, and it's bending the housing that's threaded to hold the grub screw in. Let's see this one here. That one's almost bent the opposite direction, isn't it? Well, I guess it would be bent in one way would be the other. It's just all cockeyed. They should be straight up and down, you know. But this end bell, this gold end, should be pressed flush. And it doesn't matter what I do now. Even if I take the grub screws out and push it closed, which I did previously in the previous video, it's just going to push it back forward. Now, the way that we can combat this issue is with these thrust bearings here. So the design of these is, I'm going to see if I can do this with one hand. These are 4mm, okay? And these are 5mm. They sell these in all different sizes. They sell them in 4mm, 5, 6, 8, and I think they may even sell them in like 1/8. I'm not sure about that, but I had to make sure that I got 4mm ones for my small 29mm motors. Even though when I buy these, I buy the reduction in shaft down to the smaller size. The main bore shaft of you know, the center rotor on these motors. Where's the other one at? I don't know what I did with it. They are 4mm. The shaft on the inside here is 4mm. So where it steps down there, that's why I needed 4mm bearings. So if you do order these, you're going to need to measure your shaft to make sure you get the right one. Now, we got our grooves here. See our grooves? Those grooves need to go towards the ball and face one another. Okay, so that is on there, like so. So see what that looks like? So now comes the next dilemma / problem. We have our collet here. This is going to go on. And you got to line up your grub screw with the flat spot on the motor. But if you look, the flat spot doesn't go far enough. So if we push this all the way down, we have a gap, and I think it's stuck to it. Okay, let's hold it. Let's hold it vertical to where you can get a full picture of this. See the gap in between? It's not going to do anything. It's not going to do me any good because first of all, the shaft of the motor is too long. It's too far into the collet, and the flat spot isn't far enough down for the grub screw to bite. So what we would have to do in this instance, we would have to take the motor, put it in a Ziploc bag, punch the shaft out of the Ziploc bag, and take a Dremel and cut off maybe, I don't know, how many millimeters would you say? Maybe 3-4 millimeters? Not much, just enough. You know, every one would be different. You would just have to measure it. So we would just say cut off about that much right there. And then we're going to have to take our flat spot, also with it poking out of the bag, and we're going to have to take our Dremel with a disc on it, and we're going to have to extend the flat spot to where we get the collet to push all the way against those bearings. Now, I'm going to show you exactly what I'm talking about here on the Oxydine motor, because this motor is perfect for these things, because it's got that perfect little shelf like it was made for it. So we're going to put that thrust washer there, or, you know, bearing end. We're going to put the bearing down, and we're going to take this end here. That's going to be facing it like so. The flat face goes out. Bam. So now, see how we still have the flat portion available? So we're good. Let's look at it there. We're good. Let's go ahead here. Now, if that shaft was too long, we simply put it in a Ziploc bag, poke the shaft through, and we take it to the Dremel and we cut it down. So, see what we get here? We get a nice, smooth mating of the collet to that thrust bearing. For now, when we lock this down and we bolt it into our boat, the forward thrust of our flex cable that's going to go into this collet, I don't think this cable will actually go into that collet, but plus the collet's tight right now, so it's not going to do me any favors. The inward force, the axial force pushing into the motor because of the thrust of the propeller is going to make it load up on that bearing right there, not push against the back bearing here, because what it's doing, it's taking the rotor, okay, it's taking this rotor, which has these bushings on it here inside of the motor now. Now these, you notice these are larger. These are actually made for this TP motor here. Let's go ahead and pull this off to where I can show you. Let's go ahead and we're just going to do the two biggest bushings just for video's sake. So you see that bushing right there? So that's actually on the opposite side of this, okay? It's on the other side of this gold piece inside the motor. When you load axial force, pushing now into that rotor is pushing against the end belt, and it's pushing against these bushings here, which most of my TP motors have 4 of these in the back, and they're all different sizes. So these, I believe, are bushings, and they're going to be sacrificial, because anything that's going to spin 40 or 50,000 RPM with X number of pounds of axial load, it's going to wear them out. So, you know, if we can take that, because what that's going to do, that load pushing on the end bell, on the back of that motor, is going to cause resistance. So short of adding oil to this area to help lubricate it, but that oil is only going to live so long under that amount of load and that amount of heat, because these motors generate a lot of heat. You know, the inside rotor is going to get somewhere 170 degrees. You know, when the outside can reaches 130, you can always assume that the inside rotor is going to be 40 degrees higher. That's just my rule of thumb on that anyways. Now, if you get too much heat on the inside, you lose all magnetism inside these things and they die. But this is just something that I've been thinking about, and this motor here prompted the thought, because there's a difference between radial load and axial load, and an RC car has no axial load. It's all radial load. And I believe that these motors were designed that way to be used in cars. And then, you know, brushless got into the boat market, and the boats are flying. We're doing 100 and 120, 150. Some do 200 miles an hour with boats. And there's no telling what the guys who are capable of doing 150 miles an hour with a remote control boat, the small, fine little details that these people have learned. You know, I don't know anything. I've only been messing with boats for a little over a year. So don't look at me as an expert, but look at me as somebody who's going to test it. I'm going to put it through some extreme abuse. I've taken $200 motors and $300 motors, and I've trashed them in a period of 5 days. Not proud of it, but I've done it. You know, sometimes operator error. Other times, maybe I threw too much to it. Or what I personally think sometimes is maybe the design of the motor just won't there yet. So in a situation like this, with such a high kV value and me throwing 15 volts of juice to it, and making this little $32 shrimp kit that's supposed to do 35 to 40 miles an hour, doing 2.5 times that speed with the prop and the setup I've got, I'm way, way beyond the hull capabilities, and luckily that hasn't flown apart. But that's why I bought a TP motor, was because I figured the quality of the TP motor was going to be there enough to where it could withstand that power. And, you know, I just never expected so much torque, so much axial force pushing through the motor that it's going to push the back off, push it to a load that is so much that the center can is also going with the back, and it's popped the front off. Because remember, this piece on the front, it has no bolts, it has no grub screws. This whole piece here is threaded on to this can. And when I had taken it off in the previous video, when I noticed it was loose, the same gap that you see here in the back was the same gap we saw here in the front, and it had literally pushed over the threads. Now you might say to yourself, no, it unthreaded. That is impossible. It is impossible for it to unthread simply because the front of the motor was locked stationary, and the motor wires in the back would prevent it from doing at least one revolution. There's no way the can could even revolve. There's absolutely no possibilities. With the cooling jacket on the motor and the wires and everything, nothing could spin. So the only other probable answer to that was, why was the front loose? It popped the thread loose. It pushed off one thread, which was absolutely nuts. Now, I'm not taking it off here because when I did, I took the motor apart, I cleaned it, and then I put blue Loctite all over the damn in-bell housing, and I tightened it back up. Now, in order for me to get that off, it may come off easy or it may not come at all. But with what I've got going on back here, I don't even know how much more time I want to spend trying to run this motor, because it's eventually just going to grenade itself and, you know, whatever. But I've actually got other motors that I want to test in this boat. So to conclude this video, I'll show you those motors. I've actually got another one coming, believe it or not. So I've got this motor here, which is a learner motor. This is roughly 3,500 kV. I believe it's 34.99. And then we have the 10-shock motor, which is 3450 or 3460 kV, something around that bout. So what I want to do with this motor is I want to put it in the shrimp rigger. I know it's going to go slower, but I'm honestly really, really curious how this motor is going to do in that boat. And in the future, we'll pop the learner motor in there and we'll go from there. But I tried to upload my run to speedrun.com. They wouldn't accept it because I didn't use My Gears app. Now, I could be all about the numbers and try to say, hey, you know, take it and this, that, and the other thing, and go and use the app and use this motor. I know I did 91 miles an hour. I know I did 86, and then I know I did 88, and then I know I did 91. So I don't really care if my name's not up on a board for 2024. I think we're closing on the end of the new year anyways, so I've got a whole nother year, 2025, to get on the board with some sort of boat. Whether it's a hydroplane, or whether it's a catamaran, whether it's a monohull, ready to run, or whatever you want to, say. But we'll get on the board some form or fashion. That is exactly what this little shrimp rigger is for. We're going to try to make a shrimp boat do 100 miles an hour. And I'm going to do some fabricating to make that one really, really, really strong when I build it. I got to take weight into effect, nose weight and tail weight, like weight distribution, and just overall weight of the boat. And I watched Cozy RC. He shrunk his sponsons down, which should save on nose weight. But if we make the nose weight too light, then we're going to start lifting. So there's a lot of little variations I want to do. I want to move the motor back, which is going to make it tail heavy. And then if you cut the sponsons, that's even going to make it more heavy. So there's a lot of variables that I have to take into account here when we build the next one. So I'm going to take my time with that. But yeah, so I hope this taught you something. I know I learned from it. Showed me something that I've never seen before, separating a motor due to thrust. Absolutely blew my mind. So something that'll blow my mind. It should entertain the viewers, should teach you a little bit. And if you learned something, give the video a thumbs up, and we'll see y'all on the next one. Peace.